So my paper topic is based on machine learning algorithm for non-line of sight millimeter wave in 5G V2X communication. Non-line of sight is a major problem in millimeter wave. So in this paper, we have implemented machine learning concept in order to overcome the drawbacks in millimeter wave in terms of non-line of sight. Me, Deepika Mohan, along with my supervisor, Dr. Professor Peter Chong and Dr. Nawaz Ali, we have proposed and implemented this research work. So vehicle communication sees more advancement in this technological world. So vehicles and the roadside unit communicate with each other in order to exchange information about live traffic updates, warnings, and safety messages. The main purpose of vehicular communication is safety and avoiding congestion. We all know vehicles and networks communicate with each other through cell phone towers. And since 5G is a revolution of digital world, it provides very high speed data transfer with extremely low latency of less than 1 millisecond. And also, 5G advancement has benefited in autonomous driving as it provides ultra high reliability with low network energy consumption. Here, vehicle to everything plays an important role in supporting accident free transportation, where the 5G V2X trains the vehicles to communicate with the environment in order to obtain information from the outside world. The classifications of 5G V2X are vehicle to vehicle communication, vehicle to infrastructure, vehicle to pedestrian, and vehicle to network communication. So this existing V2X technology is operated below 6 GHz carrier frequency. Here, millimeter wave bands are widely used in this kind of communication as it provides a higher data rate and a very short wavelength. Generally, the frequency range of millimeter wave ranges from 30 to 300 GHz with an available bandwidth of 250 GHz. But for 5G, the millimeter wave bands are operated between 24 to 100 GHz. The advantages of millimeter wave bands are its increased network capacity and bandwidth with reduced cell size. The frequency can be reused, and millimeter wave bands are effectively used for a group of vehicle that communicates within the line of sight. The applications of millimeter waves are telecommunications, scientific research, weapon development, medicine, and police radars, speed radars. So even though millimeter wave has seen so much of advancement and it is used in n number of applications, the major drawback millimeter wave faces is its higher penetration loss. The signal can be easily abstracted by larger buildings and also by a smaller pin. That is, millimeter wave cannot communicate with vehicles or devices that are at non-line of sight. The major motivation for this research is that there is always a higher demand for 5G V2X application that involves new design with faster transmission and reduced complexity. So utilizing the benefits of millimeter wave in V2X communication will make information transfer even more easier and faster. The objective of this proposed research is to broadcast safety messages to all the vehicles in line of sight and non-line of sight under the millimeter wave coverage area. So here, a relay using machine learning is proposed in order to train the millimeter wave base station for identifying the location of obstacles and selecting a suitable relay to communicate with devices or vehicles at non-line of sight. So finally, in order to make use of the advantages and benefits of mmWave in 5G V2X communication using machine learning, that can be enormously used in autonomous and semi-autonomous driving. So related works, so these are the related works which uses machine learning in terms of 5G V2X and mmWave communication application. So here, Q-learning is implemented in cache placement, cooperative statistics, and handover mechanism. Where in cache placement and cooperative statistics, a group of vehicle is chosen and an effective communication is done between these group of vehicles intelligently. And in a handover mechanism, the base station is switched on and off. So whenever a vehicle enters into the coverage area of a base station, the base station is switched on. Otherwise, it is switched off. So all these applications are implemented in order to reduce energy consumption. Next is deep reinforcement and Q-learning, which is used in graphical processing unit, optimal relay selection, and near prediction method. So in optimal relay selection, a best suitable relay is chosen from vehicle traveling in platoon, and from this relay, the information is broadcasted to all its neighbor vehicle. And for near prediction method, the vehicle traveling near the base station is selected as a cluster head. So from the base station, the information is transmitted to that particular vehicle, and from that vehicle, the information is broadcasted to its neighbor. And this handover mechanism is also implemented using supervised learning. But in this method, the messages is transmitted, that is, it's switched on from one base station to another base station as the vehicle pass by. So this is purposefully done for traffic application scenarios. And then the reinforcement learning. The reinforcement learning is used in trial and error method, multi-arm bandit, and cluster-based approach. In the trial and error method, for every successful action, a reward is given, and for every unsuccessful action, a punishment is given. Hence, the base station learns from its outcome. And for a multi-arm bandit, the network information is obtained from the base station through the vehicle's arrival direction. So this multi-arm bandit application is performed in order to make the base station automatically learn from its environment. The cluster-based approach, which is similar to the optimal relay selection. So here, the vehicle traveling in a platoon is chosen as a cluster head, and using a single hop or a multi-hop relay, the information is broadcasted to all the other vehicle traveling in that particular group of platoon. And finally is our proposed RML, that is relay using machine learning algorithm, which is proposed using reinforcement learning. So here a single hop relay mechanism is used for transmitting information to vehicles at non-line of sight. So this research work is done for a long-term motive, and it is basically used in non-line of sight millimeter wave 5G V2X applications. So the problem, even though more number of methods and applications are proposed to solve the non-line of sight problem in millimeter wave, it makes the system more complex. As we all know, millimeter wave is prone to blockages and it is not suitable for urban development. So there are initially two kinds of blockages in millimeter wave. The buildings are assigned as a permanent blockage and the vehicles are assigned as temporary blockage. And whenever mmBS, the mmBS is the millimeter wave base station, whenever the mmBS communicates with the vehicle at line of sight, which is far away, then the signal undergoes severe shadowing and path loss. And also the important problem of millimeter wave is that it cannot transmit data in case of rain. So one such solution in order to overcome the non-line of sight problem in the millimeter wave is by using machine learning. Machine learning trains the base station in order to identify the location of obstacle and non-line of sight node. And then an efficient relay is chosen for transmitting the message to vehicles at non-line of sight. This makes the system simple and reduces complexity. So this is our proposed architecture. So in our proposed architecture, a urban scenario is considered, so which is prone to rapid traffic changes, and the signal is often interrupted by permanent and temporary blockages. So here, the base station coverage range is set to 300 meters. A relay mechanism is used for transmitting messages to vehicles at non-line of sight. So here, a capable relay is chosen. So this capable relay should have a stronger signal strength to transmit message to non-line of sight mode. The advantages of our proposed work is that lesser deployment of base station, it is easier to formulate machine learning, which saves time, cost, and energy, and also it adapts to changes in traffic pattern. So now a question arises, how will the base station identify the location of non-line of sight node? So initially the base station will not know the location of non-line of sight node, but in V2V communication, the vehicle exchange information with each other regarding the speed, direction, and location of its neighbors. So the vehicles under the coverage area of the mmBS will exchange information with each other through V2V communication. And when the base station communicates with a line of sight vehicle, it obtains the data of all the vehicles that it does not communicate with, and hence these vehicles are assigned as non-line of sight vehicles. So here our proposed work is split it up into two stages. One is the identification of blockage and the other one is the relay selection. So how is the obstacle identified? So initially the blockages are identified using reflected radiation pattern of the antenna. A threshold value of 16 feet is set. So whenever the reflection pattern is obstructed lesser than 16 feet, the obstacle is a temporary blockage. And when the reflection pattern is obstructed greater than 16 feet, then the obstacle is assigned as a permanent blockage. So why is this threshold value is taken as 16 feet? So here an analysis is done in terms of temporary blockage to measure the height of a vehicle, and it is found that the maximum height of a truck or a semi-truck will be 16 feet. So in rare cases only we can see larger vehicles more than 16 feet entering into the urban area. But in an urban area, the maximum height of a vehicle that enters is 16 feet. So a 16 feet is taken as a threshold. So when a blockage is detected greater than 16 feet, these blockages are considered as permanent blockages. And in this research work, we consider only permanent blockages. So here, when an obstacle is identified, the distance between the mmBS and the vehicle is calculated. And using RML, the mmBS understands the best location and position to communicate with non-line of sight vehicle. So once when the blockage is identified, the position of the non-line of sight node in order to transmit information to the non-line of sight vehicle. So can everyone hear me?
Yep, we can hear you.
Yeah. Okay. So next is the relay selection. A relay is selected under three following conditions. The first one is the relay should be between the mmBS and the non-line of sight vehicle, and the relay should be within 100 meters range, because then only the signal will be strong, and then the relay node should be in line of sight with the non-line of sight vehicle. Once when a vehicle is found satisfying all these three conditions, then that vehicle is chosen as a relay. If there are two or more vehicles satisfying this particular condition, then the vehicle having the shortest path between the mmBS and the non-line of sight is chosen as a relay. And this is a RML algorithm. So only the important pseudocode of RML algorithm is presented over here. The input is basically the broadcast message. The base station observes from this environment, and when it detects an obstacle greater than the threshold, then it is a permanent blockage. But when it detects an obstacle lesser than the threshold value, then it is assigned as a temporary blockage. Vehicles exchange information with each other, and the distance of each vehicle is calculated in terms of line of sight and non-line of sight. And then the distance between the blockage and the base station is calculated as Vd is equal to dr minus gv. Once when this is done, next the relay selection. If a vehicle is found satisfying the above three mentioned following condition, then the shortest path is calculated between the relay node and the non-line of sight vehicle. If the condition is satisfied, then that particular vehicle is chosen as a relay. So once when the target is chosen, the action is performed, and for every successful action, a reward is obtained, and the state is updated. Then the RML goes in search of another non-line of sight vehicle and the relay node for its suitable communication. So RML time complexity. So the proposed RML has two types of complexity. One is the training time and the other one is the runtime complexity. For training time complexity, it depends upon the amount of data, which is larger. And for runtime complexity, it is based on the depth of traffic. Because the traffic pattern is not constant, it changes. Sometimes the traffic is lesser, sometimes the traffic is more. So hence, it suffers the runtime complexity too. And the simulation setup. The simulation tool we used is Network Simulator version 3, that is NS 3.29. So here a terrain area of 300 cross 300 was set up, and the base station is located using a constant position model, and the mobile nodes are located using a random waypoint model, where the vehicle travel freely within the terrain area without any restriction with a constant speed of 15. And the buildings are located using 3GPP propagation model, where a maximum number of buildings used is 10 and the maximum number of vehicles used is 50. The next one is simulation results and discussion. The simulation was carried out in two stages. In stage 1, the number of vehicles are made constant at 20 and the obstacles are varied from 2 to 10. With this, the output was calculated in terms of latency, throughput, and PDR. This scenario was compared with a normal mmWave scenario, which is prone to blockages and without using RML. On comparing latency, the model using RML is less than 0.5 millisecond for maximum of 10 obstacles, but it is near to 0.7 millisecond for normal scenario. Similarly, for throughput, the value reaches 29.44 millisecond for model using RML with a PDR of 100%. But the PDR is less than 35% for maximum number of obstacles in scenario without using RML. In the second stage, the number of obstacles is made constant at 10 and the vehicles are varied from 10 to 50. The output is obtained in terms of throughput, latency, and PDR. Similarly, like stage 1, for stage 2, the latency is less than 0.1 millisecond for model with RML, but it is more than 1.6 millisecond for other model. Likewise, the throughput for vehicle is equal to 10 is 19 Mbps when using RML, which attains a PDR of 75%, but the other model produces less than 40%. The outcome. Since this RML algorithm was formulated using reinforcement learning, it can solve real-world application. It can be used for broadcasting emergency and safety messages. And using a deep reinforcement learning in RML, Earlier traffic prediction and relay selection is also possible. Limitations. Since a single relay is used for transmission, the signal suffers fading. RML cannot predict traffic patterns earlier. Future work. Instead of reinforcement learning, a deep reinforcement learning will be used to further enhance the system performance. Identification of temporary blockage accurately with respect to other parameters will be made. In order to overcome shadowing and fading, multi-hop relay, that is a maximum of 2 hops, is carried out as a future work. And finally, the conclusion, a single hop relay mechanism is carried out using reinforcement learning in 5G V2X application for identification of blockages and relay selection in order to communicate with non-line of sight node. Hence, the proposed RML produced output results better than the normal mmWave scenario. That is, using RML, the maximum number of obstacles, the PDR of 75% can be achieved. And the references that I use for this presentation and for my research work. And thank you.